As a quick reminder of what those assignments are, the Moving Man assignment is due today. So at the end of the class, we'll have about a half an hour of work time. And if you have questions, you can stick around and ask those questions and get help on that. And that'll be due tonight. And then the summary sheet is due next Monday. I have to think about which, if we're on A day or B day. Due next Monday for A day classes and Tuesday for B day. And that one, you need to make sure you're watching the screencast webcast that's there on Axis, using the PowerPoint, whether it's the PDF form or the actual PowerPoint form of the notes, and completing that worksheet as a homework assignment. And remember, the Moving Man is a lab grade, so keep that in mind. And then just keep plugging away at that positive physics assessment. That will be a quiz grade that's due next Thursday for A day and Friday for B day. So you guys are A day, so Thursday for you guys. So those things are coming up. Any quick questions about timeline, schedule, when things are due before we jump into today's lesson? All right. I have one student. I still have the international students that are all signing up. They can only pick from certain days with the testing center, so they're still signing up. But I only have one student in the on-campus group that is taking the test. To be taking it tomorrow morning, so probably tomorrow afternoon I'll be able to publish the test so you can see directly and easily what your score is, and you'll be able to view then your test and see the comments and corrections. Then on Monday next week, we'll actually start going through some corrections with you. And if you do the corrections, you'll earn the curve grade. So when I publish that this weekend or whenever it happens, you'll also in the comments of the grade see your original score and the curved score. And once you've completed the corrections, the curved score will be put in place of the original. Right now, the original is what's there. So over the weekend, I plan to put those curved scores into the comments. And so that when you can see them later, you'll see both and know how that'll affect your grade once the corrections are completed. And then the retest options, like I said, I'll give you probably a couple of times and dates next week when you can choose to do a retest. And then the week after the quarter is over, you'll probably have another time or two to choose from. So that's the schedule. Let's jump into the notes. All right. I'm going to let you just read through this for a second silently, and then I'm going to comment on a few things. All right, so in this unit 3, we're really focusing in on the concept of acceleration. And the acceleration is obviously the change in velocity over change in time, like we learned in our last lesson. But here we're going to start looking at more of a graphical evaluation of it. So we kind of, in the last lesson, we defined it. We did some math calculations to practice it. But now we're going to look at, as opposed to that algebraic approach, more of a graphical approach. And we're going to start with, what if we think of this VVAT equation, this final velocity equals initial velocity plus acceleration times time? What if we think about that as actually being in slope-intercept form? As we mentioned in our notes last time, the acceleration models we look at for this class will always be constant acceleration. Therefore, your velocity time graphs will always be straight lines. They won't necessarily be horizontal, but they'll always be straight and uncurved. So because they'll be straight lines, we can instantly and directly apply slope-intercept models to the velocity time graphs. And so this is something you'll be doing frequently. You can see the relationship here if we have VVAT as our formula and y equals mx plus b as our desired slope-intercept form. If we just flip-flop the AT and the VO, it's in the exact same pattern as slope-intercept form, where the VF lines up with the y. So if we put the velocity on the y-axis, it should be the y variable. It should be the dependent variable. And then the VO lines up with the B in the slope-intercept equation, meaning the VO should be your y-intercept where it crosses the y-axis. And it should be that because if the vertical axis is your velocity, where it crosses should be the velocity at time 0, your initial velocity. And then the x variable is time. That's what we're going to be graphing on the x-axis. And if time is on the x-axis and velocity is on the y-axis, when we find the slope, we're taking velocity divided by time, and we've defined that as acceleration. So the slope ends up being the acceleration. So when we look at this VVAT equation, it really is a slope-intercept formula for acceleration if we were to graph velocity versus time. All right, so this is going to be a really important critical connection for you to make. And as we get ready to do additional labs and additional problem solving in the next several lessons, connecting the fact that velocity versus time gives you a linear relationship and understanding how we can write that as a mathematical model that follows slope-intercept form should be really helpful for you. Any questions about that before we look at a couple more specific examples and dig into it just slightly deeper? All right, so this is more in words and equations. Now let's look at it a little bit more visually. So below we can see the geometric explanation for acceleration on the right. On the left, we just have a basic line that shows us if we wanted to find the slope of that line, we would do change in y over change in x. And then on the right graph, they're just showing you, that is actually what we're doing if it's velocity on the y and time on the x. Change in velocity over change in time is the slope, but change in velocity over change in time is also the acceleration. So the slope of a velocity time graph is the acceleration. And that's the key factor here. Now, this is the second kind of graph of the three that we've looked at. We started with position time, and then we went to velocity time, and then we did a little bit of dabbling with acceleration time graphs. For this, we're saying for a velocity time graph, the slope is the acceleration. What was the slope for position time graphs?
The velocity?
The velocity. So if we start with position in time, the slope becomes the velocity. And then if we graph velocity in time, the slope becomes acceleration. So for those of you that have had calculus or in calculus, you understand we're talking about the derivatives. If we start with position time, then the derivative of that gives us the velocity. And if we take the velocity time, the derivative of that gives us acceleration. And so you understand, hopefully, that calculus connection. But what I want you to highlight here is recognizing that if we graph velocity time, then that slope is the acceleration. All right, another way to process this is just kind of rephrasing it, kind of giving you a second look at it. The graph on the right does have the slope change in v over change in t. And we know by definition that means acceleration. Therefore, this is kind of our conclusion. The slope of a velocity time graph is equal to the acceleration. So any questions? That's the first of two major topics today. All right, I'm hoping you're not only seeing the connection in this graph, but you're also seeing the big picture. Position time graph is one way to monitor and evaluate motion, where we could have a linear graph or a curved shape. And then velocity versus time is a second way to evaluate motion graphically. And we're always in our class going to have linear relationships for velocity time. And then acceleration time graphs are the third way to evaluate motion graphically. And we'll focus a little bit more on that later today. But those acceleration time graphs are always going to be horizontal lines for this course. All right, so position time graph could be curved or straight lines. Velocity is always going to be straight lines, not necessarily horizontal, but straight, constant slope. And then acceleration time will always be horizontal. All right, let's try a couple. So in the chat, look at this graph. Be careful of the scale. Look at the scaling on the X and the Y axis. And in the chat, tell me, what is the acceleration based on this velocity time graph? All right, seeing mostly the same result here as the answers keep ringing in on the chat. One quick reminder, I know in math class, you often are encouraged to write slope as a fraction. In fact, when I taught math, I did the same. But in physics, why is that a limiting factor in physics?
It doesn't show significant figures.
Good. So, and I'm not too concerned about significant figures in this example, but I just want to make sure we don't lose track of that reminder that putting the slope as a fraction in physics, while not mathematically incorrect, in the cases where significant figures do matter, we can't really see them well in a fraction. So I would encourage you to try to make sure you get into that habit of just using decimal forms to be clear on the ability to show sig figs. And then most of you have a plus sign on there. Why is that plus sign mandatory? Why is it important?
Because it shows positive direction.
Maybe. You're on the right track.
Because if it was negative, it'd be, or because it's positive, it'd be if it's negative, it's kind of slowing down. Because if you had acceleration going in the other way, but you already moving one direction, you can kind of be slowing down and then eventually turn around.
Mm-hmm. Good. There's something a little more basic I'm looking for.
Because velocity and acceleration are a vector, so you have to give magnitude and direction.
Good. So we have to give some kind of a sign that tells us whether the acceleration is opposing or not. So Andy said it tells us the direction. And on a very basic level, that's pretty right. But acceleration, it's more, how does it compare, kind of like what Cade was saying, how does it compare to the velocity? Is it opposing the velocity? Are they going against each other? Or are they helping? Like, is the acceleration assisting and going in the same direction mathematically? We can actually think about acceleration and velocity as going hand in hand when they're both the same sign, and then one affecting the other in the negative when they have opposite signs. We'll dig into that more later. But the key is that they are both vectors, velocity and acceleration. So to show that it's a vector, we don't want to just put 0.2 and have people assume that they know that means positive 0.2, that it's going in the same, or it's assisting the velocity. We want to emphasize the fact that it's a vector by giving that sign. All right, good. Let's try another one. All right, seeing pretty good consistency here as we see our answers coming through. If we think about the slope of this line, change in velocity over change in time, our final velocity is 0 if we pick that point, and our initial is -25 if we pick that point. And those 2 points are 10 seconds apart on the x-axis. So during the 10 seconds of the x-axis movement, the change is a -25 meters per second on the y-axis. And so we get a -2.5 meters per second. Quick question, do we have to choose those points to find the slope?
You can choose any points, can't you?
Yeah, why is that true?
Because it's constant. So
Yeah, good. So because the slope is constant, it's unchanging. It doesn't really matter which points we take. Those are pretty easy ones because we can see it clearly starts at 25 and we know it crosses 0 right at 10. So those are 2 logical points to choose, but you can pick any points you want. You'll get the same slope answer, which gives you the acceleration because the slope is constant. Same thing on this previous problem. I didn't actually show you the work, but here they've taken 10 minus 2 in terms of meters per second. So they've taken this very top point and this very bottom point over here to the left and shown that that happens in a 40-second time interval. But you could pick any 2 points along here. Probably most of you didn't necessarily choose the 2 points they picked. But because it's constant, it doesn't matter. The slope's still going to tell you the acceleration either way. All right, questions on how to interpret the velocity time graph to determine acceleration? All right. Let's wrap this part up and then we'll jump into the second half of the lesson today. So could I get someone to read this first paragraph here at the top?
I'll read it.
Thank you.
The acceleration graph as a function of time can be used to find the velocity of a moving object. When the acceleration is constant, the velocity is changing by the same amount each second. This can be shown on the graph as a straight horizontal line.
All right, so we began the class last couple units focusing more on position time graphs, working a little bit with velocity time graphs, and very seldom dabbling into acceleration time graphs. In this unit, we're going to be focusing more on velocity time graphs and then second level acceleration time graphs, but we won't forget those position time graphs. We'll keep coming back to those as well. So we're just going to try to make sure you're becoming more and more balanced with all 3 kinds of motion related graphs. So here we're looking at acceleration versus time and we see a horizontal line. Can I get somebody else to read the second paragraph there for us?
sure.
Thank you.
In order to find the change in velocity for a certain limit of time, we need to calculate the area under the acceleration line that is limited by the time interval delta v equals at.
All right. So earlier this semester, we learned that you could find the area under a velocity time graph. And what did the area under a velocity time graph tell us?
The position.
The change in position. Good. So position time graphs, the slope tells us velocity, then we can make a velocity time graph. If we take the area under the velocity time graph, it refers back to the position time graph and tells us change in position. See the connection? We're going one way with the slope of position time to get the velocity. We use the area of the velocity and it takes us back to the position. That's derivatives and integrals. Okay, that's the calculus connection. Now, if we start with velocity time graph, the slope tells us acceleration. So if we take the area under the curve for an acceleration time graph, that should tell us the velocity, right? The slope of one helps me graph the other. The area under that one helps me go back and figure out the change in the y variable for the other one. So these things go hand in hand. There's a lot of overlap and we can kind of go either direction. The slope of one tells me how to graph the next one. The area under that one tells me the change in the first one. Okay, so there's that connection. If we look at the area under the curve for an acceleration time graph, we're multiplying the y, which is meters per second squared, or the acceleration, by the time, which is seconds. So let's look at that a little bit closer. If we look at this example here, we can see if we're choosing to analyze the first 12 seconds. So they've shaded in this box that represents the first 12 seconds of area under the line down to the x-axis. So the vertical displace, or the vertical change, I guess, the vertical range of acceleration is from 0 to 4 meters per second squared. And that we're only evaluating it for the first 12 seconds. So the height of this box is 4 and the width of this box is 12. The height is in meters per second squared because that's the acceleration axis. And the width is in seconds because time is the x-axis. And when we multiply those, we see that the seconds cancel and we end up getting 48 meters per second. So what does that 48 meters per second mean? Someone put that into words for me. If that's my answer, what is the meaning of that 48 meters per second?
Would it be during the first 12 seconds, the velocity changed by 48 meters per second?
Yeah, exactly. So does it tell me what the velocity is at this point in time? Not necessarily, right? It depends. What it tells me for sure, what we know is it is a change of 48 meters per second in that 12-second time interval. What would have to be true for that to be the final velocity?
The object started at rest.
Good. If the object started with a velocity of 0, if it started at rest, then it changed by 48 meters per second. So it would be a final velocity of 48 meters per second. But we have to make sure we recognize that this area is how much the velocity changed. It's not necessarily the final velocity. Okay, it depends on what the initial velocity was. Questions about how to use the graph and the area under the line to determine change in velocity? All right, let's try one. The following graph shows acceleration as a function of time for a moving object. What is the change in velocity during the first 10 seconds? You can put it in the chat when you figure it out. All right, good. Seeing a lot of consistency. Is the positive sign important for this?
Yeah, because it's increasing velocity, not decreasing.
Good. Because velocity is a vector, we do need to know both direction, and in this case, we're looking at a change. So is it changing in the positive? Is it increasing in value? Because the velocity sign is going to tell us about the direction of its movement. So this plus 30 tells us it's increasing by 30 meters per second in the positive direction. So we need to make sure we include those signs on there as well. All right, that wraps up the first half. Thinking about velocity time graphs and acceleration time graphs, how they relate, how they connect to the definition of acceleration, how we can use the area under the curve for acceleration time graphs, and how we can use the slope of a velocity time graph. Anybody have anything you want to ask before we move on to the last half of the lesson? All right. The second half, the last half, obviously, is about free fall. And free fall is a very specific type of accelerated motion. In this case, we're saying that the object is accelerating because gravity is impacting it. And today, we're going to think specifically about how an object that's been thrown straight up or being dropped straight down moves in free fall. So we're not yet going to talk about something that's moving in 2 dimensions where it's got some sideways motion with, like when you throw a ball or kick a ball or something like that, or hit a golf ball. Those would have both sideways motion and vertical motion. Right now, we're not going to consider things moving sideways simultaneously. That's coming next week. This week, we're just going to focus on what if it's just moving straight up and down. So we throw it straight up and down, or we just drop it, or we launch it straight up and down. So we're just going to consider free fall in one dimension for now. I want to show you this video. It's about a 4-minute video. It's, I think, pretty interesting way to demonstrate what people theorize Galileo did, dropping objects and trying to figure out how the gravitational force field of the Earth impacts the movement of the objects. And in this one, they take a bowling ball and some feathers, and they drop them in a vacuum chamber. So let me go ahead and boot up the video here for you and get this ready and share it. All right, I'm going to mute my microphone, but hopefully you'll still be able to hear it based on the way I've put the settings.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCV 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release. Exactly. They came down exactly the same. Wow. Look. Watch right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing.
Look at that. That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down. Gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this: the reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing that the ball and the feathers were being accelerated towards the Earth. So he concluded they weren't.
All right, so a little bit of an interesting conclusion there, where he talks a little bit about Newton's theories and how Newton defined gravity based on forces, and that is the approach we're going to take in this class. But then he also talked about Einstein's theory of relativity and how that relates to the idea of gravity. That's something, if you're curious about, if you take AP Physics 2, they go into the theory of relativity and start to analyze gravity in that different way. So that's something you can look forward to if you plan to take that class in the future. For now, the key is that if you take away air resistance, then objects do fall at the same rate because they're being impacted by the same force, which is the gravitational force field of the Earth. All right, let's go back to the notes and wrap up this second half of the lesson. All right. An unsupported object falls towards the Earth with the same acceleration, or all unsupported objects fall with the same acceleration if we ignore air resistance. And for our classes, we will typically ignore air resistance because for most objects, the air resistance impact is pretty negligible. Now, obviously, if you have something that is as light as feathers with as much surface area as feathers have, then it's much more noticeable. But if you have like a golf ball and a bowling ball, even though the golf ball is far less massive, they basically fall at almost an identical rate because they're so aerodynamic, and they both, in terms of their density, mass to volume ratio, are reasonably similar. So we actually see that they don't get as impacted by the air resistance. And so that's the scenario we're going to think of, is we're going to ignore air resistance. Now, this acceleration that's caused by the force field that the Earth generates due to the Earth's mass is called the acceleration due to gravity. And in our kinematics equations that we're starting to learn, we've used the variable a for acceleration. But here we're saying that often we could just substitute g in if the Earth's gravity is what's causing the acceleration. And so you'll see often, instead of like VVAT with VF equals VO plus AT, it'll be VF equals VO plus GT. They just substitute out the A for G if gravity is what's causing the acceleration. Now, the numerical value for this acceleration caused by the Earth's gravitational force field is negative 9.8 meters per second per second. And AP College Board does allow you to round that to 10. They do, if you use 10, still consider that to have 2 sig figs. I usually use the 9.8, and on most of their rubrics, they show both. So you can earn full credit using 10, but in your labs especially, you'll probably want to use 9.8 to get a little bit higher level of precision so that your data makes better sense. For quick problem solving, just for mental math, 10 is sufficient. One of the reasons they require work is so they can easily see, did you use 9.8 or did you use 10? On the formula list that they provide, they put 9.8. So that's generally, I think, what they recommend using for free response questions. But especially for a multiple choice question, using 10 to just more quickly solve it is probably a wise strategy. Anyway, back to this. Keep in mind, all objects accelerate towards the Earth at the same rate. G is constant. Now, that's not 100% true. G is not constant. If you get far enough away from the Earth, the value changes. But for everything we would be studying, we will be close enough to the surface of the Earth. And because of the Earth's massive size, we will see G as being relatively constant. And so we'll just use that 9.8. So let's think about an object. And while this shows it going in a curved path, that's just so the line's not on top of itself. So we're still thinking about an object that goes straight up and comes straight back down. Okay, so it's kind of like just trying to show that movement a little more clearly with an arc, but it's not moving in an arc, it's just moving straight up and then falling straight back down. So if this object was thrown upward with some initial velocity, some VO value, what happens as the object goes up?
It's kinetic and energy turns to potential.
Good. We haven't even learned that yet, but if you've got some science or physics background, that is true. What else do we know will happen?
It slows down
Yeah, it's going to
As it
slow
gets higher.
down. Say that again, Kayla.
as it gets higher. It slows down.
Good. So it is going to slow down. The velocity going in the upward direction would generally be considered positive, and acceleration, because things are being pulled by the gravity of the Earth's mass downward, those have opposite signs. And so when the acceleration is opposite the motion, which is what Cade was talking about earlier today, that means the object is going to decrease in its velocity. It's going to slow down. What's going to happen at the very peak when it reaches its maximum height?
It stops.
Yeah, in terms of its vertical movement, it has no vertical velocity for that instant. The acceleration, though, doesn't change. And this is something that a lot of students get confused by. They think, well, if the velocity is zero, there can be no acceleration. But what causes the acceleration?
Gravity.
Gravity. And what creates the gravity? What's generating that gravitational force field?
Bending of space-time from a supermassive object.
Yeah, so specifically that supermassive object is?
Earth.
The Earth. And so because the Earth is still there, like just because the ball reached the peak doesn't mean the Earth's gone. So the Earth is still there, the mass of the Earth is still present, and so that acceleration doesn't change. It's just the velocity that's changing. And then what's going to happen as it falls back down?
It's going to speed up.
It's going to speed up. In this case now, the acceleration is negative, pulling down to the center of the Earth, and the velocity is also negative because it's moving downward. Since they're in the same direction, it's going to cause an increase in the speed in the downward direction. And then what happens when it lands? Well, you could answer that question a lot of ways, but what they're trying to get at is that right before it hits whatever it hits, if it's back at the same original height, it will also have the same original velocity, just in the opposite direction. So its speed value will be the same as what it was launched with. Initially, its velocity was just positive, and now its velocity is negative, but the magnitudes would be equal. Any questions about that? All right, let's look at it more as a motion map and evaluate it that way. At first glance, sometimes students get a bit confused by this motion map, so I'll try to help you see it. Let's just focus on the way up side over here. So they're trying to show you the change. So in the left part here, these black arrows and dots, that's what's actually happening. And then in the right part here, the kind of dark purple and red, those are showing you how it's changing. And so initially there's a certain velocity, but acceleration is impeding it. The gravitational force field of the Earth is causing it to decrease because it's opposing the motion. So after a second has passed, because of this decrease that's caused by the acceleration, the next V1 will be less. So then there's our V1. But acceleration is also going to be impeding it at that point in time. And so that's going to create an even smaller V2 at the next instant. And so that's here. And then eventually, all of that velocity that was supplied originally is going to be canceled out by the acceleration, just bit by bit as time passes. Eventually, all that velocity is used up as the acceleration caused by the Earth's gravitational force field causes it to eventually reach its peak with zero velocity at the very top. On the way down then, it goes from zero, but because of the acceleration, it's going to then have a new velocity. And then that new velocity is going to be adding on more velocity because of the acceleration to create an even larger velocity, which is going to be adding on even more acceleration to this velocity, which creates an even larger velocity. So they're just trying to help you kind of imagine how when the acceleration and velocity are in opposite directions, you can kind of think about how the original velocity minus the impact of that acceleration is going to help you determine that final velocity. We just need to know how long the time frame is that we're thinking about it. So kind of a motion map look at it. Now let's take more of a graphical look at it. This is again an object thrown straight up into the air. So for any object thrown straight into the air, this is what the velocity time graph would look like. And a lot of times students, when they're asked to draw a velocity time graph, they want to draw a parabola. But the velocity doesn't change in a parabolic form. The velocity is not quadratic in its relationship to time. The velocity is linear in relationship to time. And so we see an original positive velocity because right when it was launched, it had an upward positive velocity. We don't really consider how much time and effort was taken into getting it launched. So we kind of ignore that. We're just thinking when it left the hand or when it left the cannon or whatever we're talking about, what was that a velocity right when it was launched? And that's going to be positive for an object thrown straight up. But that velocity is going to decrease regularly because the acceleration due to gravity is constant. So the slope should stay constant since the slope is acceleration. And eventually it's going to hit a velocity of 0. Once it hits that velocity of 0, it's going to start increasing, but in the negative direction. So we see this constant slope of negative 9.8 meters per second squared. We see the peak of the flight right where it crosses the 0 velocity on the y-axis and the time on the x-axis that occurs. And then it starts to speed up, but in the negative direction. If it falls back down to the same height that it was launched from, its initial positive velocity will match its final negative velocity in magnitude, assuming again that it comes back down to its original height. So any questions about this graphical look at how a projectile that's launched straight up would look on a graph? All right, we're going to go through some questions here then to wrap it up. That's all we have left. That's the end of kind of the notes portion. So now we're just going to look at some questions, a multiple choice question and several math questions. So you may want to have your calculator handy and be prepared to type some things into the chat as we go. And we're going to just see if you're getting it, kind of practice applying these things we've learned today. So the first question is multiple choice. Oh, by the way, if you ever need to refer back or just want to refer back to the notes in class, always feel free to say, hey, Mr. Webb, can I have a few more seconds if you just need more time? But also these notes are on Axis in PDF form. You can find them in Unit 3. So does anybody need more time on this one? Or are we good? See some thumbs up. All right, let's move on to the first question then. So in the chat, go ahead and give me the answer here. A ball is dropped from rest and falls. Do not consider air resistance, which we'll normally do. We will normally ignore it. What is true of the motion? Is the acceleration constant? Is the velocity constant? Is the velocity decreasing? Or is the acceleration decreasing? Good. The acceleration is constant because it's caused by the gravitational force field of the Earth, and the Earth is not going anywhere. It's still there. All right. An acorn falls from an oak tree. You note that it takes 2.5 seconds to hit the ground. How fast was it going when it hit the ground? So not after it hit and stopped, but right as it started to make impact. What was its maximum speed? You probably want to use VVAT, that VF equals VO plus AT. I'm seeing pretty consistent results here. Let's take a look at the work. Remember, they often leave the F off of the VVAT for final. They often just do V, and then they put the O or a 1 on the initial, but they'll often leave the F off of the final. So you just have to assume that regular V means final. Initially, it's 0 because it's just falling. So right as it's beginning to fall, it wouldn't have started to fall yet, and it would have an initial velocity of 0. Gravity is pulling it down at 9.8 meters per second squared, that acceleration, for 2.5 seconds. 9.8 has 2 sig figs, 2.5 has 2 sig figs, and so we get a negative 24 meters per second. I think Was it 24.5? Did you guys use 9.8? I forget what I used.
Yeah, it was
Yeah.
24.5, so I rounded it up to, or rounded it down to 25, negative 25.
All right. And in this case, this is kind of a weird rounding rule. This one actually could be accepted either way as 24 or 25. Since it's exactly 0.5 with nothing after the 5, whenever the last digit is a 5 and you're rounding the digit right in front of that, you can round it to make the preceding number even. So 24 or 25 would both be acceptable values. Most times you'll see, oh, it's a 5, round up. And that's generally what I do. In this curriculum, apparently they've chosen to use that even rule, which most books don't even teach anymore. It's kind of an antiquated rule, but it is there. So when I was in school, we learned it, but that was back in the 80s. So things have changed since then. They don't typically follow that anymore. But so negative 25 would definitely be acceptable.
Mr. Webb?
Yes.
Could you please go back to the previous slide?
Mm-hmm.
Thank you.
Did you have a question about it, or?
No, I just forgot to take a screenshot of it.
Oh, well, they're all in the PDF on Axis. So you could just look at that if you want to not have to screenshot
Oh,
everything.
I didn't know that. Okay.
Yeah. I mean, you're welcome to screenshot it, but if you want to save yourself some effort, you could just open up the PDF. All right. An arrow is fired into the air and reaches its highest point 3 seconds later. What was its velocity when it was fired? All right. See most of you coming up with an answer that agrees. So in this case, our final velocity would be 0, because at the highest point, it's going to have 0 vertical velocity. And we're trying to find the initial. Acceleration due to gravity, 3-second time frame, both have 2. I think it comes out something like 29.4, if I remember, something like that. So yeah, so that would definitely round to 29. We wouldn't round that up. The only time you can ever do that even rule is if it's precisely 5 with nothing more, nothing less. And like I said, I wouldn't worry too much about that rule, but all right. A ball is thrown down off a bridge with a velocity of 5 meters per second. So this time it does have an initial downward velocity. What is its velocity 2 seconds later, assuming it hasn't hit the water yet? I'm seeing a few. Yeah, here we go. Now we're starting to get a few more people rolling in. I'm seeing a little bit of range here from 25 to 24.6 to 26. Might be that some of you are using 9.8 and some of you are using 10. Either is fine. On these, I'm just using 9.8, but we would have to say that our initial velocity is a -5 since it's moving downward at 5 meters per second. And our acceleration is also downward at -9.8 meters per second squared. And it's a 2-second time interval. So this is going to be pretty close to 20 and then 5. This is going to have 2 sig figs, so it's going to be just precise to the ones column. And then we're going to add this -5 to it. So we should have a -25 meters per second. Questions on that one? Either the work or the sig figs, either one? All right. Last two then. Here's one that's a little trickier. A rocket is fired straight up from the ground. It returns to the ground 10 seconds later. What was its launch speed? Seeing pretty consistent. Seeing pretty consistent results here. And seeing different corrections, even self-corrections popping up, which is good. All right, so if we look at this one's a little bit different in terms of the thought process. The only velocity we know for this one is what the velocity would be at the peak. We don't know what it was launched at, therefore we don't know what it would be when it comes back down. And we don't know what it would be at any given point on its way up or on its way down. So the only velocity we actually know is what it would be at the very peak. And because right now the only kinematic equation we have is VVAT, we need at least one. We need either the final or the initial velocity for some time frame. And so since the only one we know is what it would be at the peak, we could use that as either the initial or the final. It doesn't matter. When we say initial and final, we get to define what time frame we're looking at, or the problem may define what time frame we're looking at. But if it takes 10 seconds for it to reach the peak and come back down, it would only take 5 seconds to reach the peak. It should take half the time to get to the top, because the amount of time it takes to reach the top and the amount of time it takes to come back down should be equal if we're ignoring air resistance. And so actually should be equal either way, unless it's a unique scenario. But in this case, we can see that at the top, it's going to have a 0 meters per second velocity. And the acceleration is going to be negative 9.8 for the 5 seconds. Now, they have thought about it as the 0 meters per second being their final. They're just saying, well, let's just consider what it was launched at as the original, and then the final would be 0 when it reaches the top. You could have flip-flopped that and said, well, let's assume that the top is 0, and that's my initial, and then what would the final be right before it gets hits the ground again, or hits the launching pad again. And then you just have to switch the signs, because it wants the original, which would have the opposite sign of the final in that scenario. So either way is a good approach. They have just said, well, their final is the peak. And so they're solving for the initial, which should be positive 49 meters per second. Questions on that one? A little trickier. All right, let's do one more to wrap it up then. A rock falls off a cliff and hits the ground 5 seconds later. What velocity did it hit the ground with? Good. And this is basically just the same math as the previous problem, just given a different scenario. In the previous one, we thought about a 5-second duration, either from its launch to the peak or from the peak to its final position. Here, we're just thinking about from the peak to its final position, but mathematically it ends up being the same. The direction, though, is negative since it's only falling in this scenario. All right. Any questions about the lesson today? That wraps it up for us. All right, we have about 25 minutes to work on whatever it is that you need to work on, whether you need to still finish up the Moving Man assignment that's due tonight, or if you're done with that, you could go ahead and start working on the summary sheet that's due next Monday. Or if you're done with that, or you don't feel like working on that right now, you may want to work on positive physics a little bit, that's due next Thursday. So no new assignment, just keep working on those 3. And you've got this 25 minutes. I'll keep the Zoom running. So if you guys have any questions, you're welcome to hang around and ask, or even if you leave, you can come back if you come up with some questions. I will comment on the moving man on the second part. If you, depending on when you opened up the file, your file may have said to use 0.5 for the acceleration. And I think if you use 0.5 for the acceleration, it ends up hitting the wall before you reach the full 10 seconds. Just go up until it hits the wall, and you can leave the last 1 or 2 blank if you need to, because it doesn't make sense to keep graphing it once it's already stopped. I adjusted it, but I think I didn't put up the new one in time for the students on A day. So you may have that one where you run into that issue. So if that's confusing to you, just stop your data points on the second half of that lab when it hits the wall.
I already submitted mine using like the other one. Is that fine?
Oh yeah, that's fine. No problem. Yeah, I expected a lot of people would already be done with it. So I definitely don't want you to go back and correct it or change it at all. I had a couple students say, I couldn't get 10 seconds of data because it hit the wall before 10 seconds. And that's fine, is all I'm saying.
I just graphed it like it looked like that, and then it just flatlined at the top. I had 2 extra data points. Is that fine?
Yeah, that's fine. You're still showing that while it was in movement, it was not linear. And a few students have said, oh, wait a minute, Mr. Webb, it's not linear. So how do I find the slope? I'm not actually looking for a number on that one. I'm actually just looking for you to tell me that. So what's true about the slope in that case?
It's changing.
Yep, that's all I'm looking for on that question. We'll learn actually how you can find the slope at a given point in time later, but not yet. All right, so if you have questions, stick around or come and go. But if not, we're done for the day, and I'll see you next time.
Thank you.
You're welcome.
Thank you.
Thank you.
I have a question on the summary sheet.
Sure.
For pages 4 and 5, where it says like meaning of, and then like all those, what does it ask? Like what